Now let's see another example. Let's see another example, example number 3 on application of f-duap. This is number 3 in examples which we seek to use to exemplify the use of f-duap. In this example, we'll see that sometimes an obstacle has to be cleared before it is applied. Look at the question here. It says square root of 4x plus 7 all over 3 minus 1 is equal to 2. Watch this equation again. What skills do you think will be applied while you solve it? If you carefully watch that equation, you'll discover that unavoidably we're going to make a divisor become 1, that is D. Also, unavoidably, we're going to make an adder become 0. We can even do it 1 time or twice, or even 3 times, depending on how many times it is needed to be carried out in the process. We're also going to need making the coefficient become 1. All right, let us start trying to apply the first skill, which is making the divisor become 1. In the process of trying to do that, we discover that the divisor we want to make 1, which is this 3, is not free. Let's now look at the third worked example among the examples that are designed to highlight how to apply f-duap. This is the third example among the examples designed to highlight how to apply the formula f-duap for solving ordinary algebraic equations. This example number 3 says square root of 4x plus 7 all over 3 minus 1 is equal to 2. If you watch this equation carefully, you will observe that at least 3 skills will be applied. 1, if you watch that equation, the divisor is not 1. 2, if you watch the equation, you will see that the adder is not 0. We could have more than 1 adder. If you also watch that equation, you will discover that that unknown x doesn't have 1 as its coefficient. So at least D, A, C for divisor, adder, and coefficient will be needed to be dealt with in the course of solving this equation. Let us start with the first one, which is an attempt to clear the divisor to make it become 1. Unfortunately, the divisor, which is 3, is not free for clearing. Why? It is enclosed in a common root. So that means that that root has to go. If this root has to go, we also have to remember that before a root goes from a particular expression on one side of an equation, that root must be alone. A root does not go in presence of other things like adders. Before this root goes out from here, it must be the only thing on the left-hand side. But unfortunately, we still have minus 1 on the left-hand side. Before I proceed, let me make it clearer that before a root is cleared, it must be the only thing on one side of the equation. But this root is not the only thing on this side of this equation. We still have minus 1. So let us make the root be the only thing on this left-hand side. How do we do it? This minus 1 has to go. We now see 2 obstacles. The first obstacle is that the divisor, which is 3, is enclosed in a common root. And in an effort to get that root out, we discovered that the root is not alone, leading us to another obstacle which we must clear, which is -1. Now, let us first clear that -1. See how it is being done here. By now, we should have known what is happening here. I'm converting this -1 to 0. The same thing happened to what was added to the left-hand side was also added to the right-hand side. +1, +1. Obstacle to D being cleared. That is what is happening at this level. Now, simplifying this left-hand side, we are left with this. Simplifying right-hand side, we are left with this. That means both sides have been simplified. Is it now time to clear the root? That is the root alone on the left-hand side of the equation? If it is not yet alone, if you have another adder on the left-hand side, that adder has to be cleared again. The only adder we have is this +7, but it is a part of the root. So this adder will not be touched until this root is off. At this point, surely we have come to a stage where we have to clear the root. What is this? This is a square root. We must clear it. How do we clear it? Look at how to clear it here. To clear a root, use power. To clear power, use root. Now, this is a root. I want to clear it. A square root will be cleared with power 2. A cube root will be cleared with power 3. A fourth root will be cleared with power 4, and so on. This is a square root. So this power 2 will be used to clear it. After we evaluate this operation, we are going to be left with this. That is, all of this raised to power 2 is this thing inside the root sign. So this entire operation here is to ensure that that number under root sign, which is 4x plus 7 all over 3, comes out the same and without any further root enclosing it. So what is new to this left-hand side? This 2 is new to left-hand side. Does it change the value of left-hand side? Yes, it does. Because of that, the same square, or power 2, should be applied to right-hand side. That's how we came to 3 raised to power 2. 3 was there before. Because 2 was introduced here as a power, the same 2 introduced here as a power. This simplified will give us this 9. This simplified will give us 4x plus 7 over 3. Now, the two obstacles to handling D have been cleared at this point. Let's make progress. That expression 4x plus 7 all over 3 is equal to 9 can be reconstructed to appear as it appears right now. 4x plus 7 all over 3 is equal to 9 over 1. That is, the right-hand side has been reconstructed to attain the status of the left-hand side. What do I mean? The left-hand side appears like a division or a fraction. If this 9 is just written as 9 without anything under it, it appears like a whole number, which it is actually. It is 9, but for us to see it as a division or a fraction, we have to make it appear like that of left-hand side. How do we do it? Something has to appear under. That which must appear under or should appear under is not supposed to change the value of 9. So what is that that will be placed under 9 and will not change the value of that 9? Only 1. If you put something else here apart from 1, that number will change the value of this 9. But we don't want to change the 9 to something else. That is why this 1 is introduced here. From now onwards, anytime it becomes necessary to reconstruct a whole number to appear like a fraction or division, please just write over 1, that whole number over 1. Now we make progress. We should not forget that at this point, the two obstacles that were preventing us from continuing have been cleared. The root is off, and that adder that was preventing root from being removed has also been removed. Now we have to start practicing clearing each of those obstacles. The divisor is 3 instead of 1. The adder is 7 here, though later it might turn to something else. But for now, it is 7 and might even remain 7 afterwards. The coefficient of this x is 4 instead of 1. Let us start with making the divisor become 1. As before, we look for the LCM of the denominators. The LCM of 3 and 1 is what? Is 3. Use that 3 to multiply each term in this expression. That is all of this times 3, and all of this times 3. See how we wrote all of this times 3. See it here. And look at how all of this times 3 is expressed. See it here. Now let's continue. When this 3 divides this 3, the answer is 1. 1 times 4x plus 7 is 4x plus 7. When 1 divides this 3, the answer is 3. 3 times 9 is equal to 27. So what is happening here, please? What is happening here is that the divisor is being made to become 1. And here, the divisor has been made to become 1. No more divisor 3. It has become a linear equation without a fraction. Here we say that both sides have been simplified. Now, this first scale has been applied. Next is to clear the adder and make it become 0. The adder is 7. We must make it become 0. Look at it being made 0 here. I'm adding to it its inverse, which is minus 7. And so we have here 4x plus 7 minus 7. Please, what is new to this line when compared to this line? Minus 7 is new to it. What it means is that this minus 7 is brought in to achieve a goal. What goal is that? The goal of converting this plus 7 to 0. And now we know that plus 7 minus 7 is 0. Also, this minus 7, which appears on the left-hand side, which has changed its value, as we have been taught earlier, must also appear on the right-hand side. And that is why the same minus 7 appears here. So what is happening here, please? We are trying to make this adder become 0. So adder is being made 0 on this line. Now simplify both sides of this equation. Plus 7 minus 7 is 0. 0 plus 4x is this x. Left-hand side simplifies to become 4x. Now simplify the right-hand side. 27 minus 7 is 20. Right-hand side also simplified so that both sides have been simplified. Let's continue. The next is that after we have made divisor become 1 and we have made adder become 0, the last skill to apply is to make the coefficient become 1. 4 is the coefficient instead of 1. Let us make it 1. This is why 4 will divide 4. Please compare this left-hand side with this left-hand side. What is new? This 4 is new. It was brought from outside this operation to achieve a goal. that 4 was brought to make this 4 become 1, so that when 4 divides 4, the result is 1. Our intention is to make 1 become the x coefficient. And because the value will change here when this 4 is introduced, the same 4 was introduced in the left-hand side to reach 20 over 4. So when this 4 divides this 4, please, class, before we proceed, what is going on here? Coefficient is being made 1 by dividing both sides by 4. If 5 is what is here, I would have chosen 5 to divide both sides. If 3 is what is here, I would have chosen 3 to divide both sides. If 10 is what is here, I would have chosen 10 to divide both sides. But because what is here is 4, I chose 4 to divide both sides. I hope you are following the argument here. All of these were discovered through testing. We're just trying to carry out what we have learned through tests. Now, when this divides this, it is 1. 1 times x is x. Therefore, x is equal to 5. And that is our solution expressed in that form.